Alright guys, so in the previous lecture we actually talked about the introductory part of NMRO. Now we talked about the idea of nucleus having a small magnetic field around it, and this magnetic field make this nucleus to spin in different direction. For instance, if you have this as a nucleus, now we say there is a magnetic field, a small magnetic field which make them to spin in different direction, right? Now, but we said in the presence of an external magnetic field, let's say we have an external magnetic field, what will happen? This spinning nucleus can either align with the magnetic field. Let us say the magnetic field is applied in this direction. The spinning nucleus can either align with the magnetic field, that is this one here, or they can actually oppose the magnetic field. Now we say those ones that align with the magnetic field, we say they are low energy. While the ones that actually oppose the magnetic field, we said they have what? High energy. Right? Now, we also said that since we have low energy and high energy, we can calculate the energy difference between the high energy nucleus and the low energy nucleus. I will say the energy difference, change in E, is H times the frequency. Are you getting it now? Where the frequency, we said, is what we call the precessional frequency, because in the presence of an external magnetic field, this nucleus, they will precess. I've explained that before, like a spinning top, right? Now, we also said that if we actually supply radio frequency, that is the frequency of light coming from the NMRO source. Are you getting it now? The frequency of light coming from the NMRO source is called the radio frequency. We said that it can actually promote those low energy nucleus to high energy nucleus. And then after some time, they fall back, right? We've explained this before. And when we say they fall back, what happens? They emit radiation. And that radiation is what we actually detect using the detector for what? NMRO. Was that not what we discussed exactly in the previous class? Now, not all nucleus have the tendency to exhibit NMRO. Not all nucleus have the tendency to actually exhibit this spin, rather, or magnetic spin. Now, the only nuclei that exhibit NMRO phenomenon are those for which the spin quantum number I is greater than 0. Now, you must take note of this, because things like this is what we actually definitely show up in the OBJ part of the exam, right? In the objective. Now, not all nucleus actually have this NMRO phenomenon. That means this nuclear spin we are talking about. Only nucleus for which the spin quantum number I is greater than 0. So any nucleus for which the spin quantum number is less than 0 will not exhibit the NMRO phenomenon. Now, and the spin quantum number is associated. How do you determine it? Because most times it won't be given to you, but how do you now know the spin quantum number? Now, the spin quantum number most times will be determined from the mass number and the atomic number of the nucleus. The mass number and the atomic number of the nucleus. For instance, if they give you a nucleus such as, let's say, one proton. Now, we say for proton, the atomic number is 1. The mass number is also 1, right? Now, if you look at 1 and 1, 1 is an odd number. The other one here is an odd number. Now, in a situation where the mass number is an odd number and the atomic number is an odd number, this possible spin quantum number that we can have are 1.5, 3.5, 3 over 2. This is not 1/2. This is half. This is 3 over 2. This is 5 over 2. Is that okay? So in a situation where the mass number is odd, the atomic number is odd or even. Sometimes the atomic number may even be odd or even. The spin quantum number is half, 3 over 2, 5 over 2. Of course, half is greater than 0. Hence, you expect nucleus having mass number odd, atomic number odd or even to exhibit the process of what? NMRO, or the phenomenon called NMRO. Is that understood? So, now let's look at another sample, another one very well. Let's take this other one we have here. The mass number is even, the atomic number is even. Now the spin quantum number is 0. We say these ones that their spin quantum number is 0 cannot undergo NMRO phenomenon. Is that okay? Cannot undergo NMRO phenomenon. An example of that compound is, now so many of you might have been wondering, why are we not using the atomic mass of carbon that we know is carbon 12? Why are we not using carbon 12 for NMRO? Why do we opt for carbon 13 NMRO? Now this is the reason. If you look at carbon 12, it has atomic number 6, mass number 12. 6 and 12 are even and even number. That means their mass number is even, atomic number is even. So the nuclear spin or the spin quantum number for carbon 12 will be what? 0. All these are for your objective. You should take note of that. Is that okay? The spin quantum number is 0. So when the mass number is even, the atomic number is even, the spin quantum number is 0, and that cannot exhibit this NMRO phenomenon we are talking about. Do you understand? That is the reason why we went for carbon 13 instead of carbon 12. Now, if you look at carbon 13, the mass number still remains the same. What differs is the what? The atomic number, because of course they are isotope. Isotopes are compounds that have the same atomic number but different mass number. Now, if you look at this carbon 13, the atomic number is 6, even. The mass number is 13, odd. Are you getting it now? So the mass number is odd. The atomic number is what? Is even. If you see it, mass number is odd. Atomic number here is even. Now, in this case, it can actually exhibit the NMRO phenomenon. Do you get it now? So that is the general idea on NMRO, the kind of nucleus that can actually exhibit this NMRO. Now, in a situation where the mass number is even, the atomic number is odd, what do you think will happen? The spin quantum number, what do you think the spin quantum number is? The atomic number is odd, but the mass number is even. Now, it can have spin of 1, 2, 3. Is that okay? So that is that. And that is the reason why oxygen, if you look at, let's look at another compound again, oxygen 16. Let's predict it if it will undergo NMRO based on this knowledge. Now, oxygen has atomic number 8, mass number 16. Now, atomic number is what? Is even. Mass number is even. Atomic number is what? Even. It cannot undergo this NMRO phenomenon we are talking about. Do you get it now? So oxygen will not actually undergo this NMRO phenomenon. Now, the reason is because their NMRO spectrum will be much more complex than could be accounted for. Is that okay? Now, other nucleus that can actually exhibit this NMRO phenomenon are nucleus like boron 11, carbon 13. I've actually stated that nitrogen 14, and then you also have nitrogen 15. Now, if you look at these two compounds, and even phosphorus 31. Phosphorus is 15, right? Odd, odd. This one is odd, odd. This one is even, odd. Are you getting it? These all can actually undergo NMRO spectrum. Now, what do you think will be the difference between the spin quantum number for each of these? For these two, this one, the atomic number is odd. I mean, the atomic mass is odd. The atomic number is what? Even. So it will be having integers like half, 3/2, or 5/2 as the spin quantum number. Why this one? The mass number is even, atomic number is odd. So you should be expecting it to have 1, 2, 3 spin quantum number. Now, that is that. Now, let's look at the next part. Now, what happened under the influence of an external magnetic field? Now, we've actually said that in the presence of an external magnetic field, most protons can orient in just two directions. They can orient forward, upward rather, and they can what? Orient downward. Is that okay? Two directions. Now, how do we actually calculate the two directions? You say, under the influence of an external magnetic field, a magnetic nucleus can take up different orientation. The number of different orientation is given by now, how do we calculate the number of different orientation? It's given by this formula. The formula says 2i plus 1. The number of different orientation is given by 2i plus 1. Now, let us take it to cognizance. A proton. Now, the spin quantum number for proton is half. Of course, please remember that this I we are talking about here, or this I here, is actually the spin quantum number. So, for instance, proton whose spin quantum number is half. Wherever you see I, you put half. How many different orientation do you think this will now be? For proton, this will be 2. Wherever you see I, put half plus 1. Now, at the end of the day, these two can cancel these two. You are left with 1. 1 times 1 is 1 plus 1. That will give us how many? 2. So, there are just two possible orientation for proton. Now, let's look at deuterium. Deuterium and nitrogen-14, I've explained to you nitrogen-14, we have spin quantum number of 1, right? So the spin quantum number is our I value, is 1 for nitrogen-14. So what do you think is the possible orientation for this nitrogen-14? To be 2 times 1 plus 1. So 2 times 1 is what? Is 2 plus 1, and this will give us what? 3. So the possible spin orientations for nitrogen is 3. Now, same thing is applicable to deuterium. Deuterium have I is equals to 1. The possible spin orientation is also 3. Now, just try. Let's say a molecule was given to you and the spin orientation or the spin quantum number, right? The spin quantum number was given to you as 2. And then the question says, find the number of possible orientation. What do you think the answer will be? You use the formula 2i plus 1, where I is the spin quantum number. Is that okay? So, like we said, if we want to repeat what we said earlier, that only nucleus that have spin quantum greater than 0 can exhibit this NMRO phenomenon. Is that okay? Only those ones that have spin quantum number greater than 0 can exhibit the word NMRO phenomenon. Is that okay? So that is that. We'll see in the next lecture.